Hello, in this lecture, we are going to continue with the method of images. We were discussing method of images, and one of the I told you already that this particular method is based on uniqueness theorem, which we are going to discuss in detail later on. But right now, just have a gist of it. Okay, so it says that in physics, mostly we are finding solutions which satisfy certain boundary conditions, and solutions to Poisson equation or Laplace's equation in order to find the potential can be in general many. So therefore, the solution which satisfies certain boundary condition has to be, that is, no two solutions can have the uh, no two solution can satisfy the equation with a specific boundary conditions. Okay, and I also told you briefly about Dirichlet boundary conditions where the potentials are known on the surfaces, and also the Newman's boundary conditions where the derivative, the normal derivative of the potential, which is electric field, is known on the surfaces of the conductor, which are generally in direction normal to the surface. And Cauchy boundary condition would have the mixed boundary conditions, that is the normal derivatives of the potential, and potentials are supplied to you at the surfaces of the like for example at the surface of the boundary, at the surface of the various conductors in problem. Okay, so what is suggested is that if I am supplied with certain boundary conditions, my solution should be unique. So let's say I developed this kind of thought, that developed this kind of method of images, this conceptualization, by giving you infinite grounded conducting plane at infinite grounded conducting sheet at z equal to 0, and there was a point charge q placed at 0 comma 0 comma t. Since this is infinite grounded conducting plane, its potential has to be 0. Okay, and its potential has to be 0, and one can understand that even when q tends to infinity, because of this, you can understand that this is q, so therefore there would be some minus q generated here. However, this distribution is not known to you. Okay, how this kind of distribution will be there, it's not well understood. Although you can make an assertion that this q, if this is q, then obviously minus q in totality would be in totality would be induced on the surface of the infinite grounded conducting plane. Now, if you take like, if you want to write the potential at infinity, the potential at infinity due to this point charge q would be tending to 0, and due to this induced charge distribution, eventually eventually giving you a total charge of minus q, will at infinity, it will, this potential due to this induced charge would also be 0. So you have two boundary conditions. One of the boundary condition is that since this is grounded, so at z equal to 0, potential must be 0, and at infinity also your potential should be 0. So in order to satisfy this boundary conditions, what do? We replace the system by this system. In this system, what we've done, we've taken q, and instead of this plane, we have replaced this plane. We've written that v should be 0 at xy plane, and we've taken an image charge. And subsequently, we also found the potential. And you can see that the potential at any general point x comma y comma z would be given by kq upon x square plus y square, z minus d because of this, and z plus d whole square. This would be because of this my image charge. So this is the potential due to image charge. This is the potential due to the original charge. And you can see that at z equal to 0, if you place z equal to 0, this would become 0. So potential would become 0 at z equal to 0, and as z tends to infinity, or sorry, as r tends to infinity, that is x square plus y square plus z square, when it is very, very larger than d square, that is this, like x square plus y square plus z square is very, very large than this distance between the plane and this charge q. Or you can say that x square plus y square plus z square, if they go on towards infinity, this particular term would become 0, this particular term would become 0. That is, the potential satisfies my initial boundary conditions. Okay, so given, if I have replaced this system by this particular equivalent system, my boundary conditions are unperturbed. So boundary conditions are being satisfied. So you can, instead of solving this problem, you can solve this problem. What is the advantage of this? Because you can clearly see that this kind of induced charge distribution, without knowing this induced charge distribution, you cannot know what is the force exerted on this charge q and various other things. So first thing that we found out in the previous lecture was induced surface charge distribution, which appeared which can be found by simple calculation. That is, electric field near the surface of the conductor is given by sigma upon epsilon. And if you want to find that, you have this potential and the normal derivative of the potential. So normal derivative of the potential, because the infinite grounded conducting sheet is on the z equal to 0 plane. So therefore, normal to it would be the z-axis. So minus del v upon del z at z equal to 0 would give you sigma upon epsilon naught. And you can clearly see that the sigma would be minus qd upon 2 pi minus qd upon 2 pi x square plus y square plus d square raised to power 3 by 2. And if you want to write all these things in polar coordinates, instead of x square plus y square, you can also write r square plus d square. Total charge also be calculated, which can be induced on the infinite grounded conducting plane by simply integrating by induced charge distribution sigma r comma theta, and you can find that total charge induced is minus q. And what would be the force that this charge q would experience because of this? Because you can clearly see that if had this been there, like this plane would have been there. So therefore, because of q, there would be opposite charge induced on the surface, and because of which it will appear, it will feel a force. So we replace this problem by this particular problem, and this particular problem only there is a you can see that there is a charge minus q. So instead of this, we have this. Now this charge q would feel force because of this image charge, and it's fairly simple to find that the force would be kq square upon 4z square, and at z equal to d, if it's placed, then it will be k minus kq square upon 4d square k cap. And similarly, we found potential energy due to this configuration. So overall, this was all that we were doing in the last class. Okay. Now, let us do a few more things today. One of the thing can be, see, one thing is very clear that because of this charge q, which is placed in front of my infinite grounded conducting plane, minus q, that is in totality, would be induced on the surface of the conducting plane. Since minus q is induced, so you can clearly see that it will feel a force. It will feel a force towards the. It will feel this charge q would feel the force towards the conducting sheet, and because of this force, there would be a time when it will hit the plane. There would be a time when it would hit the plane. So usually one can think of that what should be the time in which the charge q hits the plane, provided it is released from the rest at a distance d from an infinite grounded conducting plane. So this is our query, that if this is the charge q, it is placed in front of an infinite grounded conducting plane. So infinite grounded conducting plane means your potential is 0 here. So because of this potential, because of this charge q, there would be some negative charge densities that is induced here. So this negative charge density would be induced. And because of this negative charge density induced on this infinite grounded conducting plane, this will feel attracted towards this infinite conducting sheet. Since it is attracted towards this infinite conducting sheet, so you can expect that this would hit the plane at some point of time, and we want to find that time in which this charge q would hit the plane. Okay, so this is our query. So let us do it. Okay, so let us consider that at any point let us consider that at any time t, my charge particle q is at 0, 0, z. मान लेते हैं ऐसा कुछ है. What does it imply? Just because this is kinematics, one has to keep care of the signs. So like this is k cap and this is minus k cap. Okay, so the force on charge q is equals to this is k q square upon 4z square, and this will be in the minus k cap direction. And what is fz? Fz is equivalent to writing mz double dot. Okay, so I'll write simply mz double dot. So I'll write it as mz double dot is equals to minus kq square upon 4z square. So this is increasing direction, sir. So this is increasing direction, sir. So this we have taken positive. Okay, so now you can understand that in order to because we are given that initially our speed was 0. So what we can take, we can transform this particular thing. So I'll transform this particular thing in terms of the speed. So m d2z upon dt square is equal to minus k upon 4z square, and this is q square. So instead of writing this, I'll do certain manipulation. That is, I'll do this. Okay, and what is dz by dt? Dz by dt represents instantaneous speed. So instantaneous speed of the charged particle of mass m and charge q would be let's say I'll write it as b. So this is mb, and this is what? This is dv by dz minus kq square upon 4 square. Now you can see that if I try to integrate this up, I'll get the velocity, I'll get the speed. So what is the speed? Why I'm not using term velocity? Because I've already taken in account the directions. So don't worry about it. I'm just considering what is the support, because in one dimension there can be only two directions. So I've already taken in account by putting this negative sign here. Okay. So what would be the speed? This will be v dv minus kq square upon 4z square dz. Okay, and if I integrate this up, and this m would also come, sorry, so m would also come, and if I integrate this, I'll get v square upon 2 is equals to k q square upon 4m z plus some constant of integration, and I know that at z equals to equal to d, that is at initial time, my particle was released without any initial velocity. So it was since okay, since charge q was released from rest. Okay, so I'll use this initial condition, and because this value would be 0, so c would come out as, I'll write c would be v square by 2. This is kq square upon 4mz minus kq square upon 4. It is quite easy to find. I'm leaving this as a calculation for you. Okay, so eventually my my speed would be equals to root over k q square upon 2m, and then this would be 1 upon z minus 1 upon. So this is my speed. Now you will be saying that why did I not put plus and minus sign? So speed, I'm taking it as positive. Now, if you say that why not negative, so I'll take in account of what speed is. Okay, so don't worry about it. But right now, you should understand that speed is a scalar quantity, and so therefore I've taken it in magnitude sense. Okay, now understand this charged particle is executing motion in this direction. So executing motion in this direction, your dt would always increase. So if you release your particle from rest, obviously in due course of time, your dt would increase because time has to increase anyway. But because of increase in time, dz is less than 0. You can see that in this direction, your z coordinate decreases. Your dz should be negative. Now, what is speed? Speed is dz by dt. Okay, but in modulus. Okay, so the speed is modulus. So your dz is in this direction is negative. So I'll supply a negative in front. I'll supply negative in front of it in order to make it positive, because you should understand that if this particle is moving in this direction, then dz would be negative, dt is positive. So overall, this dz by dt would be negative. But you can see that in magnitude sense, v has to be positive. So I have written minus dz by dt has to be equivalent to writing root over kq square upon 2m, and then I will write 1 upon z minus 1 upon d. I hope it is clear till now. Okay. So what I would do, I would write this. This is like root over 2m. No, I'll keep this here only so that it doesn't bother you. So I'll take this pair. So I'll only take the function that are different. So I'll write z d divided by d minus z root over, and this is dz integration, and this is dt. Okay. Now, if my particle starts motion at t equal to 0, at that particular time your z was equal to d. So at time t equal to 0, your z was equal to d. And when it will hit the plane, z would be equal to 0. And here t would be, let's say, tau. So this is the tau, is the time when it hits the plane. hits the plane z equal to 0. So at time t, at time tau, your charged particle would hit the plane. Okay, is that clear? I hope it is clear. Now, what can one do? Here, in order to solve this particular integral, one can resort to substitution of d sine square theta. So I'll replace z by d sine square theta. And what would be dz? Dz would be 2d. So this will be sine 2 theta d theta. And if I put z equal to d, my lower coordinate, well, what you can say, my this coordinate would become pi by 2, this would become 0. So I'll write 0 to pi by 2 instead, and this I'll absorb this negative sign. And this will become, I think, zd. So you have one d from here, because if you replace d here, this will become d square sine square theta upon d square cos square theta. So you'll get d. I will write 1 so that I don't get confused. So it will be d. Okay, this d would get cancelled. This will be cos theta from here. And dz would be d okay, there would be some d also, right? Because there is root d, root d, root d. So 3 to power d by 2. So you can see that here you would have d, d sine square theta. So d minus d sine square theta would give you d cos square theta. And here you would have again d. So one d would get cancelled, root over d will be left, and one dz you have this again d term. So you have this d by 3 by 2. And here you will get k 2 square upon 2m. And this will be simply tau. And this will be root over, sorry. Okay, so overall, one can understand that this is like d to power 3 by 2. Integral, if you can take this from here, so it will give you 2 times sine theta. So you'll get integration 0 to pi by 2, 2 sine square theta d theta. And this is root over kq square, root over kq square upon twice m tau. One can clearly see that this integration from 0 to pi by 2, 2 sine square theta can be written as integration 0 to pi by 2, and I can write it as 1 minus cos 2 theta d theta. And obviously, this will give me some pi by 2. Okay, because this cos 2 theta will become sine 2 theta, integral from 0 to pi by 2, give me 0. So in a way, I will write it as 2 d to power 3 by 2 into pi by 2. Not pi by 2, sorry. I think, yeah, pi by 2. Okay, that is fine. Because 2 sine square theta I have written as 1 minus cos 2 theta. So this would be pi by 2. And you have this root over kq square upon pi some tau. So at the end, I should write my tau, which is the time required to hit the plane, is given by, I think I will get, I'll write the entire thing up first. So this is d. So I'll write d inside. This is pi. So this will be pi square. This is 4. So I mean 2. So I'll write it 4. And all these things will go inside 2m divided by k, and that will be q square. This is your tau. Okay. So this is how your tau. Or if you want to solve it all the more, then I think I should write it as d cube. Then I will write pi square. Then I will write 2. I will write m divided by 4 into 1 upon 4 pi epsilon naught, and then I will write q square. Okay, so this 4 gets cancelled. You have this pi which will go up, this epsilon naught which will go up. So eventually, time required to hit the plane, I am writing here. Time required to hit the plane z equal to 0 would be what? It would be equal to tau, which I will write root over 2 dq pi square m, sorry, pi cube, my mistake, epsilon naught. So this is 2 pi cube dq m epsilon naught divided by 2 square. Okay, so I don't know if you can remember this or something, but this is the result. I mean, this is the result. This is the time this charge particle q would take in order to hit the plate. I hope it is clear. So I think this is quite clear to you. Now, what one can do, is okay. What one can do is I think I should take some problems, and then we should be able to get the things. Okay, we should be able to get the things once we are done with the problems. Okay, so when we are done with the problems, we will be able to get the things. Okay, so okay, so let us do that problem also. Let us start doing some problems. Okay, so it will give you some sort of the first problem that I'm giving to you is very simple. It's only based on formula only. So most of the time you'll find in exams also. This is quite easy topic. Even without knowing the concept of image method, people do these problems very easily because they have certain realization that what needs to be done. So you know that what needs to be done is just replace the original problem by putting an image charge. So instead of q, you have this image charge minus q placed. Okay, so this is how you do your problem. So this is what I'm going to, first question that I'm going to take is based on that only. That is complete formula based question. So what is that question? Question says that a point charge is located. So I'm writing PT means point. A point charge is located at a distance d, at a distance d above a grounded infinite conducting plane. So I have this point charge which is located at a distance d above a grounded infinite conducting plane, and let P be the foot of the perpendicular. So let P be the foot of the perpendicular position of the charge on the plate. Now one asks that find the radius of a circle centered at P, in which 1/4 of all the induced charges you make. Okay, so what is being asked? It is being asked that, let us say this is your charge particle Q. It is placed at a distance d. It is placed at a distance. So this is my charge particle Q. And it is placed at a distance d. This is 0, 0, d. So it is placed at a distance d from an infinite grounded conducting plane. So this is my infinite grounded conducting plane. So this is my infinite grounded conducting plane. Okay. So I'll write this here. So this is my infinite grounded conducting plane. Okay. And what I can do is, I know that the total charge induced due to this charge Q is given by minus QD upon 2 pi x square plus y square plus d square raised to power 3/2. If you don't remember it, I'll show you the result quite quickly. We have derived this result. We have derived this result, I mean, somewhere. Okay, so we've derived this result somewhere here. Okay, this is minus QD upon 2 pi r square plus d square raised to power 3/2. So this is what we have derived. Okay. So now what it says is, it says that because of this charge q, obviously there would be some induced charges. So I'll write again, make the diagram. So this is my z equal to 0 plane, and because of this charge q, there would be induced distribution of charges. So because of this, let's say this is your foot of perpendicular here. So this is, let's say, P. It says that what would be that radius? What would be that radius where till that limit of radius, the induced charge, total induced charge, is 1/4. Total induced charge is 1/4 of the total charge it would have induced. So basically, what one wants to ask is that what would be that radius where total charge induced would be minus q by 4, because 1/4 of the total charge induced, one can see that in previous problem I have discussed that if this charge q is there, so total charge that would be induced on this plate would be minus q. Since total charge induced would be minus q, one wants to ask, one is asking that what would be the radius where your total charge induced would be minus q by 4. Is that clear? This is a very easy question. It's just a formula question. So one can see that if I integrate this sigma dx into dy, I should get minus q by 4. Where if I integrate this in this particular region, okay. So instead of using these coordinates, I use simply different coordinates. This is r dr d theta, and let us say that this radius is capital R. So I'll write capital R here, and 0 to 2 pi, and this will be equals to what? It will be equals to minus q by 4. And this integration, it's very easy to see that this will be integration from 0 to r. This is sigma. What is sigma? This is minus qd upon r square plus d square ki power 3 by 2. This is 2 here. I'll supply, and this will be simply integration from 0 to 2 pi is 2 pi, and there's half I've done here. Okay, and there is r dr. So what I've done, I've multiplied with 2 and I've divided by 2. Okay, is that clear? So I've multiplied it by 2 because this will want me to multiply by 2, and this is minus q by 4. So overall, one can see that this integration is equivalent to writing 1 upon r square plus d square. So this is, I'll write it here. Let r square plus d square be equals to what? T square. So this is 2r, dr would be 2t dt. So this integration would be 2t dt divided by t cube. So this is 2 upon t square integration, which is minus 2 upon t. So this is minus 2 upon t. So this is 2 upon t. What is t? This is this. And this entire thing, this negative will get cancelled from here. So I'll write 1 upon 4 here. This pi will come out. So pi is there. This 2 is here. Fine. 2 is here. And d is here. So don't write this here. D will be here. Okay. And this is from, there is charge q also. Q also is here. Okay. I think there was 2 pi somewhere also. So there was some 2 pi also. I think there would be 2 pi here also. Okay, sorry, my mistake. So there would be 2 pi here as well. What mistake I'm doing, I don't know. Okay, so understand the fact that this is 2 pi. Okay. So I made this mistake. This half will not come. Sorry. Because see, integration d theta would give you 2 pi. I have taken 2 here. So if I multiply 2 here, so I'll have to divide by 2. So this 1 by 2 will not come here. Sorry. So sorry, 1 by 2 will not come here. So I'm not writing 1 by 2 here. I'm not going to write 1 by 2 here. 1 by 2 here. I'm not going to write 1 by 2 here. Okay. So eventually, what I'm left with is this 2 pi would come out in division. 2 gets cancelled. Okay. And this limits of integration would be from 0 to capital R. Okay. So eventually, this pi would get cancelled. So you have this QD, and this is 1 upon root over r square plus d square minus 1 upon d is equals to 1.4. What one can do is probably I can take this q in. I mean, this q gets cancelled. Sorry, q also gets cancelled. So this q gets cancelled with q, and what one finds is that d upon root over r square plus d square is equals to this minus 1 would go there. So this would be like, I think there should be 5/4 there, if I'm not wrong. So if I want to find this d, so I'll square it up. So on squaring, I'll get 16d square is equal to 25 r square plus 425 d square. I think there's some mistake somewhere. I don't know what is the mistake. Okay, if I square it up, is there a mistake somewhere in evaluating some integration? So let me recheck it. Okay, so sigma dx dy is minus q by 4. Okay, so sigma r dr d theta would be minus q by 4. So what I have done is I have written this minus qd. Okay, so this is okay, sorry. So this is minus q by 4. There's a negative here, so I've taken this negative common out from here. Then I forgot to write this negative here, so there would be a negative here. There would be a negative here, so there would be a positive here. So I think this should be, this is the mistake. So this is like minus d, and this would be, I think, 1/4. So this would be minus 3/4, I guess. So this is 1/4 minus 1. So this would be 3/4. This get cancelled. This is 16d square. Okay, so this will be 9r square, and this will be 9d square. Okay, sorry. So 9d square, so this will give me 7d square is equal to 9r square, or in other words, I can write my d would be equals to, or r would be equals to, sorry, r would be equals to root over 7d upon. So r would be root over 7d upon. So this is your answer. Okay, sorry for the mistake that I did between the calculations. Okay, so this is how you do your questions. Okay, so now let us do a few more questions in order to solve the grasp on this particular subject. And let us start with a few easier questions, and then we'll keep on increasing the level as we go on. So let us consider the case now. Let us consider the case of a small ball. Let us consider a case of small ball which is suspended over an infinite horizontal conducting plane as shown. So let's say this is the ball which is suspended over an infinite horizontal conducting plane. So this is infinite conducting plane. Okay, and now what what one can do is let us say that this thread, by means of which it is suspended, this thread has a stiffness constant K. So let us say that this thread has a stiffness constant K. Now, as soon as the ball is charged, as soon as the ball is charged. So let's say initially it was uncharged, and let's say as soon as it is charged, it is descended by x centimeters or x units, you can say. It is descended by x units. So now infinite horizontal conducting ground, you can write grounded here. Infinite grounded. Okay, so this is infinite grounded conducting plane. And initially it was uncharged. Now it is supplied some charge q. Okay, and now initially it was, let's say, at x naught, and now it is descended by some distance x. It is descended by a distance x, such that its distance from the plane, its distance from this infinite grounded conducting from the plane, this infinite grounded conducting plane, I mean, becomes L. Okay, we want to find what is the charge q. What is the charge q by which the ball is charged? So we want to know what is that charge q by which your ball is charged. Okay, so let us do this problem. So one can see that this ball is suspended. Now initially at equilibrium this was at x naught. The stiffness constant is given by k. Now if at all it is further taken displaced by distance x, then the net force it feels. Okay, you have to ignore gravity here. Ignore gravity here. Okay. So if it is displaced by further x, so it will feel a force in upward direction that is equals to k of x. This is very much clear. Now also understand this is it was charged q. It was charged q, and only then it was charged by a charge, let's say q, and only then it was pulled down by a distance x. So it will feel a force kx in the upward direction. Also see that this is an infinite grounded conducting plane, and once it was displaced by a distance x, the distance between this charge and this infinite grounded conducting plane became L. This is what it is written. So I'll replace this problem by writing that there would be an image charge. So there would be an image charge which is actually placed here at a distance L. So what is the FBD, that is the free body diagram of this q like? So it is displaced by a distance x. Obviously it will feel a force in upward direction, that is kx. And obviously it will also feel this force, and obviously it will also feel this force, this electric force in downward direction, which is k q square upon 4l square. This q I don't know, this q I have to find in terms of all these quantities. And this k is stiffness constant, and this k I'll write it as q square upon 4 pi epsilon naught, so that it does not confuse you. Okay, so now according to this question, your kx must be equal to what? It must be equal to q square upon 16 pi epsilon naught L square at equilibrium. Because this is what it is given, that if it is displaced by a distance x, the net distance between the charge q and the plane remains L. So at this particular point, you can say that the total force that is being exerted on this charge q are two. One force is due to this thread of stiffness constant k. Another force it is subjected to is the electric force due to this image charge. So I can write my q should be equals to what? My q should be equals to 16 pi. This k is a different k, don't worry about it. And there would be L square also. There should be epsilon naught also. Okay, so this is what it is. And there should be x also. And this entirely root over. So you will get 4L root over pi epsilon naught k and x. So this is your total charge q that should be supplied to this ball according to these conditions. I mean, You can take this. I mean, this is a question from IRUDO. Okay. So IRUDO, there is a problem with this book. Mostly English has not been well translated. Like this is a Russian book in general. Uh, so there may be problems with the translation. So I would recommend that I have the old book. If new book is there in the market, you can purchase that book. So this is very good book for at least teaching 11th and 12th standard kids. Okay. Okay. So now let us do a few more questions and then we'll see how to proceed further. So now I'll take another question, and this question is slightly different one. And this says that I'll give you this question. So consider, you can take it as a theory also. Consider a very long straight thread. Consider a very long straight thread which is oriented at right angles to an infinite grounded conducting plane as shown. So what is shown, that there is an infinite grounded conducting plane here, and perpendicular to this in the plane itself there is a very long thread, and it is at a distance. I'll write it here. It is at a distance. One end of it is at a distance L, and it carries a linear charge density lambda. This particular thread carries a linear charge density lambda, and the nearer end is at a distance L from the infinite grounded conducting plane. So this nearer end is at a distance L. This is at a distance L. Now, what one needs to find is, let's say this point is O. So I am interested in finding first, what is the surface charge density of the at point O? What is the surface charge density induced at point O? And another one can find what is the induced surface charge density as a function of distance from O. Okay, so these two are the queries that one needs to address. Okay, so this is quite easy to see that this is an infinitely long thread carrying its charge density lambda. The nearer end is at a distance L from this infinitely grounded conducting plane. I need to find what is the potential, what is the surface charge density induced at point O, and then also I need to find what would be the induced charge density as a function of distance from O. Okay, so let us do this one. So as I mentioned, I'll replace this problem. We will replace this problem by an equivalent image by equivalent problem having image charge. So what I'll do, instead of like, so this was my infinite grounded conducting plane. So instead of this, I will write that my potential should be zero. And how it would be zero? It would be zero by simply making an image of this infinitely long carrying a charge density lambda, this thread. So I think somebody would get confused that why did I make it long or that. Okay, so this is okay. Okay, so this will carry a charge density minus lambda. So this will carry a charge density minus lambda. So this is your image. You can see that this is your image line of charge. This is your image line of charge. And this is your normal, like whatever is there. So this is your charge density. Okay. I'll write it lambda here. Okay. Now, this is at distance L. So what I'll do, I want to find what would first see, what is the strategy? If I can somehow find what is electric field exerted on at point O, what is the electric field at point O? So near a conducting plane, the normal component of electric field is given by sigma upon epsilon. And from this, I'll be able to extract my induced surface charge density. From here, I will be able to extract my induced surface charge density. Is that clear? So what I'll do, I'll take a differential element from this particular thin line of charge, or you can say whatever, like image line of charge. And you can see that if at this point, if because of this line of charge, the force will be in this direction. Or you can say that because of this line of charge, if I take this, I'll take this x, and this is differential element dx, and this is charge dq. Because of this charge dq, if the electric field is in this direction, because of an equivalent, if you take dx here, this will be minus dq. You will find that again, there would be another force. So you will have 2 times. Okay, you will have net force. What I want to explain is that, say, this is your charge dq. Because of this charge dq, electric field at this point would be in this direction. And similarly, if you take a symmetrically placed charge minus dq, like if it is x here, this would be minus x and this would be dx. So if you take another minus dq, again, there would be a force in the field at this point will be again in this direction. So there will be twice the field. So whatever I'm calculating, I'll multiply by 2 in order to get the net field at point 2. I hope it is clear. Okay. So now what I'll do, I know that because of this dq, electric field at point O, I'm first writing for this, it would be equals to K, which is 1 upon 4 pi epsilon naught dq upon this distance. I think this distance was already given as L. This distance was already given as L. So let me take something different. So I'll not take this, otherwise this would be slightly trickier integral. Let's say it is at distance x only. Okay, so this distance I know this is L. So I'll simply write dq upon x square. Is that clear? So from origin, if I take, this would be dq upon x square. So this distance is L. Don't forget this distance. Okay. This is the net field at point O in this direction due to this charge dq. Okay. And what would be the total field? So total field at O would be 2 times 1 upon 4 pi epsilon naught dq upon x square, and this has to be integrated. So I'll integrate it. So what would the integration would be? Integration would be integration 1 upon 2 pi epsilon. And what is this dq? dq would be, I think, lambda dx divided by x square. And your x varies from where? This nearer end is at distance L, and your farther end is at distance x equal to infinity. And this entire thing should be equal to sigma upon epsilon naught. This entire thing should be equal to what? Sigma upon epsilon, because near like in this direction the electric field is there. So near a conducting surface, the normal component of electric field is given by sigma upon epsilon. Okay, so this is given by sigma upon epsilon. So let us write it in a better way. So this will be minus lambda upon 2 pi epsilon naught, and this is 1 upon x. So I'll take this negative. I'll get 1 upon x. This will be L, and this is infinite, and this is sigma upon epsilon. Epsilon get cancelled. So what is sigma? So sigma you will get simply lambda upon 2 pi L. So this is the surface charge density which would be induced at point O. So this would be the surface charge density. I'll write induced charge density, induced surface charge density at O. Okay. Now, instead of O, if someone asks what would be the induced surface charge density as a function of distance from O, so I'll have to take some distance from O now. Okay, so this is what was asked. I think if you